Hey guys, today I want to talk about formation and dissociation constants, Kf and Kd. So these are both expressions that we can use to talk about solutions in equilibrium, where we have two ions or more that are basically forming an inorganic complex, and our Kf will basically tell us the equilibrium constant for that complex in solution. In other words, how much of the ions by themselves combine to make this complex. So for example, we could basically have a cobalt 2+ ion and then 4 isocyanate ligands. And then this can be in equilibrium with a complex where we have our cobalt in the middle and then the 4 ligands attached to it. So overall, this will have a 2- charge on the complex, since we have a -1 charge on our isocyanate and then a +2 charge on our cobalt. So if we wanted to write an equilibrium constant for this complex forming, we basically would write our products over reactants. So here our product is that complex. So this would be the cobalt isocyanate complex. And then our reactants are a cobalt 2+ ion and 4 of those isocyanate ions. So this would be essentially what our equilibrium constant would look like. And then if we set this to whatever value, let's say 10 to the third, so that would basically tell you how much the equilibrium would favor the formation of that complex. So since this value is greater than 1, this would mean that this formation of the complex would be more favorable at equilibrium. So then we sort of have the opposite of the formation constant, which is the dissociation constant. And this is also known as Kd. So if we were to take the same ion complex that we just talked about in the previous slide, this would be our cobalt NaSCN isocyanate. And we could say that this would be in equilibrium with a cobalt ion dissociating and then 4 isocyanate ions or ligands that are dissociating. So if we wanted to write our equilibrium constant for this expression, we would essentially just flip it and take the inverse. So our new products would be our cobalt 2+ ion and then our isocyanate ion as our products, and then our reactant would be the starting ion complex. So then if we were to figure out the value for this, it would also be the inverse of the formation constant. So it would be 1/10 to the third. So basically this is telling us that since the dissociation constant is much less than 1, that only a small amount of this ion complex in solution is dissociating. So if we wanted to consider a question using this information to solve how much of that free cobalt ion would be left over in solution after some of this complex has formed, we can use an ice table in order to determine that. So what we want to do first is technically not at equilibrium, because we're going to consider how much of the starting materials we have, and based off of that, we will be able to determine how much of that complex we have to start off with that will then be at equilibrium. So I'll kind of explain this as I go, but this first ice table is essentially not at equilibrium, but it'll tell us how much there is to start off. So if we consider the formation to start off, we would have our cobalt 2+ reacting with the isocyanate. And there are 4 of these. And then this would be in equilibrium with the cobalt complex. So if we fill in our ice table here, I is for initial, so how much initial material is there? So we'd have 0.05 moles to start off for cobalt, and then we have 1.25 moles of isocyanate. And one thing to mention here, based off of what's given in the question, we're only really going to consider the two ions that are forming this complex. So even though we have a nitrate ion and a sodium ion, those ones are not involved in the formation of the inorganic complex. So we're not going to worry about those in our calculations. So to start off, we would have 0 moles of our complex. And then for this calculation, we're basically just going to assume that whatever the limiting reactant is just going to react fully. And from that, we'll be able to determine how much of the complex is formed. So here, because cobalt is the limiting reactant, we have the smallest amount of cobalt. So that's going to determine how much product we get. So we'll subtract 0.05, and this will be times 4 because we have 4 stoichiometric equivalents of isocyanate, and then we will add 0.5 moles as our product. So then if we go ahead and sum up all of our columns here, so we get 0, 1.05, and then 0.05. So now we know basically this, like we said, is not at equilibrium, but these values will be what we plugged in order to determine the equilibrium amounts. So what we're actually going to do from this point on, we're going to retain all the values that we calculated for the reaction and how much of the isocyanate's left over and how much of the product is formed, and we're going to use that in our equilibrium calculation. So now we're basically going to use those same values that we just calculated in our equilibrium calculation and determine how much of that cobalt ion will be left in solution. So we actually want to go the opposite direction of what we went in the original portion. So now we're actually going to start off with that complex formed and go backwards. So now we want to know how much of the cobalt will be dissociated from that original complex. So now filling in from what we calculated previously, we have 0.05 moles, 0 moles, and 1.05 moles. So then we're going to subtract x plus x and then plus 4x. And then essentially we will be solving for x in order to determine what that amount of cobalt is. So if we sum up our columns here, we have 0.05 minus x, and 1.05 plus 4x. So then, if you recall from our previous example, since we're going in the opposite direction now, we are talking about the dissociation constant, since we have an ion complex, which is now forming back into its individual ions. So that dissociation constant is going to be our products over reactants. So on the top, we will have the cobalt 2 plus ion, the isocyanate ion, and then our complex as the reactant. So now that we've filled out our ice table, we can just use those same values to plug in to our equilibrium constant. So our top portion will be x times 1.05 plus 4x to the fourth. And our denominator, we're going to have 0.05 minus x. And this will be equal to 1 over the kf, which is 1 over 1 times 10 to the third. And from here, all you really have to do is just solve for x. And one thing that we can make our lives a little bit easier with is to get rid of the x values in this quotient. So basically, because of the size of KD being relatively small, we can go ahead and just ignore the plus 4x and the minus x, and these will essentially not affect our overall answer. So we can just make it a little bit more simple by disregarding those. So if then we are able to go through and calculate, we should get 1.215x over 0.05. And this will equal 1 times 10 to the third. So then basically our answer is 4.115 times 10 to the negative 5 molar. And this is equal to our concentration of cobalt ions in solution that would be left over. So it's basically just a really small amount of that ion that will be left floating around in solution, but the majority of our concentration is the actual complex. So hopefully this helps you guys. These problems can be a little bit tricky at first to figure out what the correct order of steps are, but it really helps to just go through and get practice with these. So I can probably make a few more videos with these type of questions because I think a lot of times people get sort of stuck on these. So I'm happy to go through more examples if you guys want. So if this video helped you guys out, I'd really appreciate a like, comment, and subscribe. Please feel free to comment other questions or problems that you would like more help with, and I'll catch you guys on the next video.